Assalamualaikum warahmatullahi ta'ala wabarakatuh, and a very good morning. We are still in Module 4, Research Methodology and Design. This is part 7 of the module where I'm going to share with you about statistical analysis method. This is directly related to the quantitative data analysis that we have talked about in part 6. There are some important statistics concepts that we all need to know. Statistical features, probability distribution, dimensionality reduction, over and undersampling, and Bayesian statistics. First, statistical features. Statistical features are widely used in computing research and often is the first technique researchers apply when they want to explore the data that they have collected. And this include bias, variance, mean, median, and percentiles. Probability distributions. In computing, probability distributions are quantified on a scale from 0 to 1, where 0 means an event will not occur and 1 means it will definitely occur. A probability distribution is a function representing the probabilities of all possible outcomes in an experiment. So we can have discrete distribution or continuous distribution as shown on the slide. Dimensionality reduction. If we have collected our data, or if we have a data set and our data set have high dimensions, we would like to reduce the dimensions for our experiments, for example. In computing research, the number of feature variables can be reduced using dimensionality reduction techniques. One of the things that we can do if we have two sample classes. For example, we have one class that is very few and another class that has high number. So what we can do to balance both classes before we put the data into our experimental methods is by removing samples from the majority class, or we can oversamples or add samples to the minority class. But what we can do is we can do bootstrapping to oversample the minority class so that the number of data in both classes are almost or equivalent to one another. Bayesian statistics apply probability to statistical problem by allowing for updating of belief based on new data. For example, based on past event, we have the probability of an event occurring based on how many times the event occur in the data that we have collected. But after we collect new evidence or we get new information, then we can update the probability that we previously have by using Bayesian statistics. This is where we update our belief based on new data. In using statistics for computing science research, we can use descriptive statistics or inferential statistics. This is directly related to the statistical features that I've explained earlier. Descriptive statistics analyze data using charts and tables, while inferential statistics draw conclusions through hypothesis testing. For example, you have a population and you have construct your sample or taken sample from the population. Then from the sample, you apply statistical measures to get statistical features about the sample. Then the statistical measures or features that you obtained from your sample can be used to infer statistics about the actual or original population from which the sample was taken. Why is it useful to use probability or statistics for computing science research? Because if you use probability and statistics, it can help you get insights from your populations, and you can predict what will happen, and also you can do a number of estimation based on the statistics that you have applied to the sample of your data. Probability and statistics is useful for computing science research because it can help you get insights about the data that you have collected. It can help you predict what will happen in the future, or what will happen if you have or you observe a number of features or variables in your data, and it can help you estimate a number of variables, especially dependent variables pertaining to your population. So the concept is you have data where real world generate data that you can analyze using statistics. Then you develop models where you use statistics based on your data to generate probability models about your data. Then, from the models that you have developed, you can predict or make prediction about events in the real world that actually is the real data or population that you want to study. But you apply statistics only to the samples that you have obtained from the real world based on models that you have developed, to help you predict what will happen or what can happen in the real world. Descriptive statistics help describe and summarize data. It helps researchers to present information meaningfully. This simplifies the data interpretation and visualization. There are three main categories of descriptive statistics, which are frequency distribution, measure of central tendency, and also measures of variability, which I'm going to explain later in this part of the module. So in frequency distribution, you can have categorical frequency, which is used to display data in specific categories, such as nominal. For example, you have different country, different gender, race, blood type, etc. about the data that you have collected, or it can also be ordinal level data. For example, you can have income, and you can have income that is less than 50,000, between 50,000 to 100,000, or over 100,000. So you have this category of data. For example, we surveyed 25 army personnel to test what is their blood type. So we have a number of raw data, and we can count how many personnel have type A, how many personnel have blood type A, how many personnel have blood type B, and so on. So we can calculate the frequency and the percentage of personnel which have the different blood types and show it in the form of table. We can also have ungrouped frequency. When we use ungrouped frequency, basically we display data in the form of individual points, whether the individual points is in the form of values or numbers. So in the slide that I have shown, we can see that, for example, we try to study the marks obtained by 15 students, out of 25 full marks. So we count how many students have got 12 marks, how many students obtain 15 marks, and so on. This is ungrouped frequency. Or we can have group frequency. Instead of counting the number of students which have individual marks, we can display data in the form of class intervals. For example, how many students have marks between 0 to 20, 20 to 40, and so on. So we can calculate the frequency based on the groups of the classes, group of the class that we want to study. We can visualize our data using various graphs and charts, which I've explained in the previous module, such as pie chart, line chart, histogram, bar chart, and box plot. Statistical inference use data analysis to conclude a probability distribution, such as testing hypotheses or estimating parameters. The central limit theorem, CLT, is a key technique in this process. So we can draw appropriate inferences about the characteristics of the population by taking sample and then apply statistics or statistical model on the sample of the population, which can help us infer what actually happened, or we can use the models that we have developed on the sample to explain or describe about the population that we want to study. What is the central limit theorem? As your sample size increases, the distribution of sample means approach normality, regardless of the population's distribution. Typically, a sample size of 30 is sufficient for central limit theorem to apply. Central limit theorem states that sample means and standard deviations approximate the population. So let's talk about confidence interval and hypothesis testing in inferential statistical categories. Confidence interval. Confidence interval is the range within which your estimate is expected to fall a certain percentage of the time if you repeat the experiment or resample the population. If you create a 95% confidence interval, you expect the estimate to fall within this range 95 out of 100 times. The confidence level is typically 1 minus an alpha value used in statistical tests. For example, use of alpha 0.05 makes the confidence interval 1 minus 0.05. 1 minus 0.05, which is 0.95 or 95%. So, for example, you survey 100 Malaysians and 100 Singaporeans about their YouTube watching habits. Yeah? And that is the frequency graph that you have plotted based on the data you collected from the survey. So how do you calculate the confidence interval? For you to calculate the confidence interval, you need to know the point estimate you are constructing, the confidence interval for, the critical values for the test statistics, the standard deviation of the sample, and also the sample size. In the YouTube watching example, the point estimate is the mean number of hours watched. For example, for both Malaysia and Singapore, the mean number of hours watched from the data that you have collected is 35. There are 3 steps to find the critical values. First, you have to choose the alpha value. Then decide if you need a 1-tail interval or a 2-tail interval. And then you can look up the critical value that correspond with the alpha value. So if your data follow a normal distribution, or if you have a large sample where n, or the data that you have collected, is greater or equal to 30, that is approximately a normally distributed data. So you can use the Z distribution to find your critical values. Yeah, so I have given there, for example, for confidence interval 95%, the alpha value for a 2-tail confidence interval is 0.025, and the Z statistics is 1.96. Yeah. So most statistical software will have a built-in function to calculate the standard deviation. But to find it by hand, you can first find your sample variance. Then you can take the square root of the sample variance to get the standard deviation. Sample variance is defined as the sum of squared differences from the mean, also known as the mean squared error, as shown on the slide. Most statistical software will have a built-in function to calculate your standard deviation. But to find it by hand, you can first find your sample variance, then take the square root to get the standard deviation. As shown on the slide, the sample variance is defined as the sum of squared differences from the mean, also known as the mean squared error. So here, in the YouTube watching survey, the variance of the Malaysian estimate is 100, while the variance in the Singaporean estimate is 25. By taking the square root of the variance, give us the sample standard deviation for both Malaysian estimate and Singaporean estimate. We have 10 for the Malaysian estimate and 5 as the standard deviation for the Singaporean estimate. So in our survey of 100 Malaysian and 100 Singaporeans about their YouTube watching habits, we find that both groups watch an average of 35 hours of YouTube per week. However, the Malaysian people surveyed had a wide variation in terms of the number of hours watched compared to the Singaporeans who watch all similar amount. So here we can see, although both groups have the same point estimate where they have same average number of hours watched, the Malaysian estimate will have a wider confidence interval compared to the Singaporeans estimate because they have a wider or more variation in the data as shown on the slide. So you cannot just use point estimate or average here in reporting the data, but you also have to use the standard deviation or variance to compare the data that you want to analyze. To calculate the confidence interval, we need the sample size, which is the number of observations in our data set. In our YouTube survey, for both Malaysian and Singaporean, the sample size is 100. In normally distributed data, we have a bell shape when we plot the graph, with the sample mean in the middle and the rest of the data distributed fairly evenly on both sides of the mean. So the confidence interval for the data which follow a standard normal distribution is as shown on the slide. Normally distributed data forms a bell shape when plotted on a graph, with the sample mean in the middle and the rest of the data distributed fairly evenly on both sides of the mean. The confidence interval for the data which follow a standard normal distribution is calculated as shown on the slide, where the confidence interval is based on the population mean, the standard critical value of the Z distribution, the population standard deviation, and the square root of the population size. So, for example, in the survey of Malaysian and Singaporean YouTube watching habits, we can use the sample mean, sample standard deviation, and sample size in place of the population mean, population standard deviation, and population size. So, to calculate the 95% confidence interval, we can simply plug the values into the formula. So when we have plugged in the value for both Singaporean and Malaysian, we can see that for the Singaporean confidence interval, the lower and upper bounds of the 95% confidence interval are between 34.02 and 35.98. Whilst for the Malaysian, the lower and upper bounds of 95% confidence interval are 33.04 and 36.96. So when you want to report the confidence interval, you should include the upper and lower bound of your confidence interval. Okay. For example, we found that both the Malaysian and Singaporean average 35 hours of YouTube watch per week, although there are more variation in the estimate for Malaysian as compared to Singaporean. So when we want to plot the differences between groups or plotting a linear regression, researchers will often include the confidence interval to give a visual representation of the variation around the estimate, as can be exemplified on the chart shown in the slide. If you want to report the confidence interval, you should always include the upper and lower bound of the confidence interval. So in our example just now about the Malaysian and Singaporean hours of YouTube watch per week, there are more variation in the Malaysian sample compared to the Singaporean sample, and this should be shown on the graph. So One place where you can show the differences between the two groups, or when you are plotting linear regression, you should always include the confidence interval to give visual representation of the variation around the estimate, as can be exemplified in the chart shown on the slide. Yeah, where you not only show the average, but you show the upper bound and lower bound of the confidence interval of the data that you want to analyze or you want to compare. Next is hypothesis testing. In hypothesis testing, you have two competing hypotheses. One is the null hypothesis and the other one is the alternative hypothesis. And you have to collect data to evaluate evidence that can help you determine which of the hypotheses is true. Hypothesis testing is a statistical method to determine if the sample data provides sufficient evidence to draw conclusions about a population. It helps researchers assess the statistical significance of their findings, and it is crucial for validating outcomes in systematic investigation. In hypothesis testing, there are basically 5 steps, which may vary in different experiments but generally follow these steps. The first step is where you have to formulate your null hypothesis and the alternative hypothesis. Then you have to collect data in a way designed to test your hypothesis. In the third step, you perform appropriate statistical tests on the data that you have collected. And in the fourth step, you decide whether to reject or accept your null hypothesis. And in the final step, you present your findings in the results and you discuss about the results in the discussion sections. So these are the basic 5 steps that you can use to analyze your data. So in conclusion, there are many statistical measures that can be used to analyze quantitative data. And you can perform descriptive statistics or inference statistical analysis to help you answer your research question or test your hypothesis. Thank you.